so I can share with Suhani. All right. Hey, morning. Were you surprised by the phone call this morning? No, I was a little surprised, but I see that we finally have some precipitation happening here in Palmer Township. So maybe you do at your house too. The Zoom day at home isn't all bad. What we're going to do today is look through section 611. The good news for us is that it's review. We've already talked about this in the last unit, which is pretty nice. In place of, or in addition to the book problems, I was able to pull some from Delta Math as well. I know some of you are taking advantage of that. It's just preference. I decided that it doesn't matter to me if you want to do the Delta Math problems where you know you get them correct right off the bat, or if you want to try those book problems, which are a little bit more challenging sometimes that you have to think through. But I would like everybody to make sure you try the AP practice problems. Last night, I got through about the first 3 homework assignments. I need to check my answers on those, and then I will post them in Google Classroom. No, not Google Classroom, in Schoology, so that you guys can check your work as you go. Can't think of anything else that you need from me right now? Okay. So we are going to go up to 611 and the trapezoid method. Try this a little fast there. All right, so we're back to approximating integrals. Our textbook put trapezoidal sums in this particular unit, even though we've already discussed them. There's something called the midpoint rule and Simpson's rule. And the reason why these are marked out with a strike through is because they're not AP topics. So we do not have to worry about those for the AP exam. Trapezoids, though, I want you to feel really familiar with. So just consider this a chance to get to know them even better and do even better with them. So area of a trapezoid, if you remember, is 1/2 height base 1 plus base 2. And we are used to this orientation of it, especially from geometry. But when we're talking about trapezoid sums, we tip it on its side and it looks like this. So again, we're going back to those rectangles that we had. And sometimes we had a left rectangle, sometimes we had a right rectangle, sometimes we had a midpoint. This is our trapezoid rule where the top is slanted. Simpson's rule is a thing. And if we were taking a college calculus 2 course, we would definitely talk about it there. But Simpson's rule has a curve at the top, so it's even more precise than the others. So let's talk about a few formulas here. So instead of finding just the full trapezoid, they can also be found by using your left Riemann sum and your right Riemann sum. And all of this notation, this is our trapezoid formula. This notation on the right with the sigmas, this is the average of the left and the right. And I don't think I ever really took that into consideration, but if you take the left Riemann sum and the right Riemann sum and you add the two together and then divide by 2, that's your average, you get the same result as the trapezoid sum, which when you write it out, it makes sense. But is it necessary? Is that something that you have to do? No. So it's kind of an alternate method. I'm going to go back to just plain old trapezoids because instead of doing a left sum and a right sum, I may as well just jump right into the trapezoid. So example 1, use trapezoidal sums with 4 subintervals of equal width to approximate the integral from 1 to 2 of e to the x over x dx. Express the answer rounded to 3 decimal places. Remember, the AP exam is always 3 decimal places. So the first thing that we want to find is our delta x. And we remember that's b minus a over n. For this problem, what do we have for b and a? You tell me.
2 and 1.
2 and 1.
2 and 1, 1 and 2, perfect. So 2 minus 1, and then how many subintervals do we have?
4.
4, exactly. So I know that this has a delta x of 1/4. Now, for the trapezoidal sums, I know it's 1/2 height base 1 plus base 2. And it would be 1/2 height base 1 plus base 2 for the next trapezoid, et cetera, et cetera. And I know we discussed this in class, but you can actually factor out the 1/2 h. And in this case, h is really the width, which is our delta x. So I'm going to pull that to the front. I have a 1/2. My h is the delta x, which you just told me is 1/4. Same thing as h. And then we're going to do the trapezoid. So I'm going to add the two heights. So the first one, and maybe I don't know what that actually looks like to graph it, but I can draw myself some trapezoids so I remember what's what. I'm going from 1 to 2. We know each one is 0.25 wide. So for the first trapezoid, I know the height on the left comes from f of 1. And where would the height on the right-hand side come from? F of, you tell me.
1.25.
Perfect, 1.25. That's my first trapezoid. The second one, the left-hand side is f of 1.25 because it's where I left off in the last one. Plus, what's the right-hand side for this trapezoid? That's okay. My dog decided he wanted to join us today. F of 1.25 on the left and F of 1.5 on the right. That's the second trapezoid. The third one would be F of 1.5 plus F of 1.75. I'm going to group this together as well. Plus the last one is F of 1.75 and F of 2. I know that's a lot of writing. I know that's a lot of parentheses, but do you remember where those come from when we were talking about rectangles and things like that? If you want to give me a Zoom thumbs up, that would be cool. Or Zoom thumbs down. Hey, there's a thumbs up. All right, there's a few more. Okay. Excellent. Okay. So it's the same thing with trapezoids. Now, I know we discussed this part in class too at one point when we first talked about trapezoids in the last unit, but these double up. Those shared sides, you have two of. And so when you think about a trapezoidal sum being the average of the left and right Riemann sums, that makes sense. If we did a left Riemann sum, we would use f of 1 and 1.25 and 1.5 and 1.75. And then if we did a right, we would use 1.25, 1.5, 1.75, and f of 2. So all those inside values do get used twice. So mathematically, it just works out to be the exact same thing. But again, the trapezoids make a little bit more sense to me. I like to see the individual pictures, but I know that some of you are great with formulas, so you can average the left and the right. Now, my online calculator, my computer calculator is not working very well to show you, but what are you going to do with your calculator with f of 1 and f of 1.25? What do you do with these numbers? How do I turn those into y values? You're going to go back to your original function, which even though we didn't write it as f of x, is e to the x over x. So f of x is equal to e to the x over x. So you're going to replace x with 1, 1.25, 1.75, 2, and go through and figure out what all of this is. When you're all done, it's 3.069. So I know I can't walk around the classroom and see your calculators, but if you're with me, you have your notes and your calculator. Why don't you take a minute or two and try to fill those in? I'll see if I can do this with my calculator not crashing. Actually, I'll use my regular calculator. I'll show you a shortcut. Okay. I'm assuming we're still working out there. So I am going to see too far, too close, maybe like this. I can actually use the table in my calculator to come up with those values for me so that I don't have to type them in each time, which is kind of nice. If you're interested, I went into my y equals. I typed in the function. Then I went to table set, which is the blue button F2. Sorry, it's F2. And then up here, table set. Over here, table set. I wanted my table to start at 0. And then I had it step up by 0.25. That's the delta x that we just found, 0.25. And I chose to start at 0. I could have chosen 1 because that's the first value that we needed, but I just wanted to see what's happening on either side. I left it on auto. And then I went over to second table. And I have those values. So I can take the values right off the table and put them in my trapezoid formulas to get them all together. The only problem with the table is there's only so much space in each column. So if you're dealing with really large numbers, you run out of space. But because we're dealing with numbers 1 through 10, we have enough of those decimal places. Remember, we need 3. So this one works out pretty well. So if you're comfortable with a 3.069, if you've gotten that, just give me a thumbs up in the Zoom emojis. If you need me to do something else, give me a thumbs down. All right. I believe from earlier, this was like 1/8. And then this piece on the inside, we wound up around 24 point something, maybe. And that's how we got the 3.069. Any questions about that one? Okay. And if you have a question, you're more comfortable just in the chat, that you can do that too. My chat window is open. So we're going to hop over here to example 2. Approximate the integral from 1 to 3 natural log of x dx, rounded to 3 decimal places, using 5 intervals of equal width with a left Riemann sum, a right Riemann sum, a trapezoidal sum, and technology to approximate the integral. This would take a little bit of time, but I'm pretty confident that everybody there would be okay with this. So give me a thumbs up if you could do the left Riemann sum with a delta x. I think, oh, there's a couple thumbs up. Okay, cool. Give me, oh, lots of thumbs up. Give me, what, do we have a smiley face in there? It's been a while since I've done Zoom. Give me a smiley face if you could do the right Riemann sum. This one's a thumbs up. Smiley, oh, there's a laughing face. Lots of smiley faces. A teeth face. All right, cool. Smileys if we could do the right Riemann sum. Check. The trapezoidal sum, which again we did do in lesson 6 or unit 6 part A, and we talked about a little bit now. What else do we have for emoji choices? Oh, party sign. All right, party sign if you can do a trapezoid sum and you're pretty comfortable with that. Excellent. And I think there's a clapping one, isn't there? There's a clapping emoji. Do the clapping one if you're cool with technology. Yay, clap. And just remind us all, what technology are we using? I know we're using the calculator, but what do we have to go in there and do? Math, and then 9. We all clapped, so I'm assuming we're pretty comfortable with that. Okay. All right. Awesome. Then I'm going to skip that. I'm going to trust that you can do that. And if, hey, in your free time today, you want to go back and do that example, you can. But I do think we should do example 3, and this is the last one. The velocity in meters per second of an object in rectilinear motion is expressed at times t in the table below. Approximate the net displacement of the object from 1 to 10 using a trapezoidal sum with 4 intervals. We're still going to use the trapezoid, but you have to do them as 4 separate trapezoids, and that's because they all have different widths. We don't have the same delta x, so that delta x formula doesn't work. So what we need to do is go back to that trapezoid formula, 1/2 height, base 1 plus base 2 for all of these. So I'm going to have you just shout out the numbers. I know it sounds weird on Zoom, and it's okay if you overlap. Nobody's going to be offended if 2 people or 3 people or 4 people say it all at the same time. I'm good with that. I know the first one is 1/2. The height is the distance between here and here. So what's the height of the first rectangle?
1.
1, perfect. Thank you. And even though I said rectangle, it's a trapezoid. And then what are the 2 heights that we're going to use?
4 and 7.
Perfect. The next trapezoid is 1/2. What's its delta x or its width?
2.
2 is perfect. And what are the 2 heights we use?
7 and -2.
Awesome. The third one, what's our delta x?
4.
4 is great. And then what are the 2 heights we use?
-2 and 0.
-2 and 0. And finally, the last one is 1/2. What's the width of each trapezoid?
2.
2, good. And then what are the 2 heights?
0 and 3.
0 and 3, good. Now, on that last test that I graded, any mistakes that I saw were trying to use maybe the actual x values here instead of the difference between the x values to give the width. I had just a handful of people do that. And then the other one would be not so much on this version, but the first version, where we forgot to take this x value and put it into the function to get the y. Those were really the 2 biggest mistakes. But overall, you guys are doing great. We have a great grasp of what this is. So go ahead, let's figure out what the sum is. And then that will be it for today. Let's do this. All right, I wound up with 19/2, which is the same thing as 9.5. What would the units be? We're integrating, what are we integrating? Meters per second.
Meters.
Meters, awesome. So the displacement is 9.5 meters. Let's add on the time piece as well. So 9.5 meters displacement over what time interval? T equals what to what?
1 to 10.
1 to 10 is perfect. Awesome. Awesome. So Venus, this is pretty much review. It was a pretty good lesson to talk about on Zoom today.